Hey everybody, it's Elisa, and I just wanted to take a few minutes and give you this little tutorial. It's a review of chemistry and some of the basic principles of how electricity works and kind of, what it is. Since we're going to use this a lot in cells, like this is what drives so much of what cells are able to do, and in terms of at least neurophysiology, which we're studying right now, it's super duper important. All right, so the first thing I want to talk about is opposite charges. So when I say that, I want you to think of one thing. Magnets, right? So remember magnets? Yeah, not the ones on your fridge. Although those are good too. I'm talking about these ones that are like this, right? Here's a positive end, here's a negative end, right? And you would do things like, hold on, I gotta erase something. Okay. You would do things like, put another magnet up against it, and if it was like you put a positive next to it, and then they just like repel and they push away, right? And you couldn't get them to stick no matter what. But then you, being like, just a so smart kid, it was always fun to be able to flip it. And then all of a sudden, when you have opposites, they attracted, right? They got, they came together. And so that's kind of an interesting property in our universe, and cells use it too, right? And so if you look over here, here's our positive and our negatively charged. Let's get with are positively, and they're attracted, and they all, yes, they want to, be close. So that is an important thing because remember we were talking about those axons and how they're charged? Well, if you look at this, here's a whole bunch of positive ions, and guess where they're going to collect? They're going to collect towards a negative cell. So just think of it this way. Here's like a cutaway. Like if here's an axon, right? Here's like where we cut it, right? And then that's what this picture is. And you can see, this. We're looking down here, like after a sagittal cut, maybe. And so what happens are these neurons, they fill their axons with all these like little negative, right, charges. And so no matter what, like wherever they are in whatever, type of part of your body, all of the fluid and all of the ions are going to kind of float to and fro. And what's going to end up happening is these positively charged ions, things like sodium for sure, definitely potassium, they're going to be attracted to that arm, okay, of that axon. And so that's where we get these. They just actually are just kind of floating around in the interstitial fluid, and they collect there, okay? And so if you did something, if you found and stuck, like say a big needle, for example, right? And you sent an electric charge in here, there would be reactivity because you have all of these charges already, right? That's electric-like signaling, and that allows us to use energy to propagate these nerve impulses, okay? So if you were to stand, if you were just like, a little person and you were floating around on the inside of a cell membrane, and let's say you were like right here you are, you're going to stand here, and you're just like, you'd actually feel this almost kind of crushing sensation of these two charges as they're trying to get closer to each other, right? There's this tension, and that's the type of energy. The type of energy it is, we refer to as potential energy, right? So that's that potential energy. So if you were floating around, say, anywhere else, like over here, you wouldn't feel that same crushing sensation, right? But if you were right in the middle, like between these two charges, you would feel that. Again, that's that potential energy. So let's talk about some definitions. And since we're talking about energy, oops, gosh, my timer. Since we're talking about potential energy, I'm trying to keep these short, so I had to do a timer since I'm chatty. Voltage is how we're going to measure it, right? And so when we're talking about things like cells, you're used to like, oh, well, I got a 10-volt battery over here, right? Maybe not for a cell, maybe for like a little neuron, right? You're looking at like not just volts, but maybe like millivolts, like tiny, like voltage units, okay? So we're going to measure how much voltage we have, like say in an axon, using millivolts, okay? And that's that potential energy, that crushing that we find between the two different sides of the membrane, okay? So it's the potential energy. We're using those millivolts right here. And the greater the charge difference, the higher the voltage, meaning the more powerful, right, our shock can be. Another thing I want you to know about is current, and I want you to know about resistance. Okay, so a current is like water, right? Like think of water. Okay, and it's just like flowing, and sometimes the current moves fast, and sometimes it moves slow, right? Same thing happens with electric-like or electric charged ions, right? So like electricity itself actually is just defined as like, I believe, electrons moving over distance and time, right? So if it's a lot of electrons that are moving really fast, wow, that's like a big fast current. But if they're moving really slow, they're not, that's not a strong current, that's a weak current, right? So flow is dependent on voltage, which we looked at, so how powerful the voltage is, but the next thing I want you to look at is resistance. So resistance is the hindrance to the charge flow, meaning that like if you had, here's like a mountain, right? Here's this mountain, and there's two streams. Like here's one stream, and there's another stream, but maybe the second stream has like, all kinds of, I don't know, like boulders and rocks in the way, and maybe like it kind of starts like, instead of being like completely straight and linear, maybe it kind of curves around them, right? Oh, it's everywhere, right? So this one would be fast, and this would be slow, because stuff's resisting its ability to go fast. And those things are usually going to be like an insulator, okay? So that's got a slow current, right? So we wrap things like our copper wire in insulator. So we don't want, our current to hop out of the wire, right? We want it to stay and go wherever we want to direct our electricity, okay? So there's that idea. However, a conductor would be, say, for example, the copper wiring itself. Oh, it's really fast. It's like a super slippery slide. So now it's able to really kind of focus on the directionality and the power and force of that directionality. Okay, so those are some major concepts. The last thing I want you to think about is this thing called Ohm's Law. And so what this Ohm's Law does is it tells you kind of like, and it's an equation that you can use if you want, but you don't have to. It's totally not on the test. It's not on your test, but it will be in your physics class, not your anatomy class. Current is just how much voltage there is and how much resistance there is. If there's a ton of voltage and not a lot of resistance, it's going to go pretty fast. You're going to have fast current. However, if you have like not very much voltage, only a few ions are really moving, and they got a lot of rocks to get past, it's going to be a really slow current. You understand what I mean? Yeah. So when you're talking about like current, what we're talking about is we'll refer to it like as amperage, right? So that would be it. Okay, so that's all I really wanted to cover. Just a little bit of background that hopefully will help you or stimulate your memory so that you'll kind of understand how we're doing these, especially important with like excitatory postsynaptic potentials and inhibitory postsynaptic potentials, right? Those things that kind of start up action potentials or like make it harder to get into action potentials, which we'll talk about a little bit later. All right, I hope that was helpful, and I hope you're having a wonderful day. Bye.